Right, good evening, everyone. And today we welcome you to CAWASA's webinar series of 2025, number 9. And today we have with us Mr. Bu Lam, who's based in Kitchener, Ontario. And he's going to tell us about never let a good crisis go to waste. And he will tell us about how a sanitary sewer failure helped shape Kitchener's waste infrastructure program. Of course, I must do first a little introduction of our guest speaker today. He is an experienced and passionate water professional. He applies his almost 2 decades of industry experience in his current position as Director of Sanitary and Stormwater Utilities at the City of Kitchener. In this role, he combines his drive to advance technological and business innovations with sustainable community services. He actively champions water equity and community engagement initiatives and sits on various national committees advancing water management practices. Bu holds a doctorate in environmental chemistry from the University of Toronto and brings a wealth of life experience from his travels abroad, including over 6 years living and working in the Canadian Arctic. Outside of work, Bu enjoys spending time with his family playing sports and is a big foodie. Welcome, Bu, to us in the Caribbean. And we certainly would have wished to share with you some of our warmth, but we may have to do that virtually. Over to you.
Thank you very much. Thank you for that welcome. And I sincerely wish I could provide this presentation in person because it would have been great to be in the Caribbean right now instead of here in Ontario. So I will load my slides really quickly here. Give me 1 second. And hopefully everyone can see that. Oh.
Yeah.
Sorry, can people see the presentation?
Yeah.
Yeah, you might want to just put it in
in
presentation mode, though.
Yeah. Sorry. How's that?
Great.
Okay, excellent. So today I'm going to be presenting on a case study that we had from a sewer failure and how that crisis that, at the time, required a lot of response and a lot of emergency response, road closures, things like that. How we took that crisis and we actually turned it into something that was positive. So not really taking that crisis, letting it go to waste, but really using that as a springboard for us to advance a more sustainable program going forward. So really quickly, just some information on kind of where we are in Kitchener. So here's just a quick map of Canada. We're located in the province of Ontario. So that little dot right here near the bottom, just above Washington, D.C., that's Kitchener. We're about 100 kilometers west of Toronto. And, everyone in Canada, everyone around the world often thinks of Canada as, kind of the Toronto being the epicenter. So we often use reference to Toronto when we're talking about where we're located. So the CN Tower is kind of where that arrow is pointing, and Kitchener is approximately 100 kilometers west of there. So we're a little bit further away from the lake. The city itself has a population of over 300,000 people. And that translates out from a sanitary service perspective to about 65,000 customers. The assets that we have for the sanitary utility total just over $2 billion. Our service area is about 107 square kilometers. And throughout that service area, we have 23 pumping stations, about 834 kilometers of water mains, and then 105 kilometers of trunk sanitary sewers. There's also 13,000 manholes that we have to service as well. So just quickly, I wanted to describe our approach to services and how we deliver our wastewater services. So when we're talking about our capital and our pipes, most of our pipes are actually replaced through a linear asset replacement program, which are essentially full road reconstructions. So we call it our triple funded utility replacement program. What this means is that the water infrastructure, the sanitary infrastructure, and the stormwater infrastructure, so the pipes that are all residing underneath the road surface, they typically will get replaced all at one time. So, if we're excavating for one utility, we usually take all 3 utilities at the same time. And that just makes sure that, we're able to keep the pipes that are in the worst condition rehabilitated as much as possible. And then it also gives us an opportunity to fix the road surface. So typically we would do about 6 kilometers of full road reconstructions on an annual basis. We prioritize most of our projects from age and material. And if we have condition information that's available, we usually apply that condition information as well to make some of those decisions. So a pipe that might be, let's say, 80 years old might be in better condition than a pipe that's 60 years old. So in that case, if we had condition information, we would prioritize the 60-year-old pipe before the 80-year-old pipe for replacement. We try to do our utility inspections as often as possible, but admittedly, it is fairly infrequent right now. Our CCTV program only looks at pipes once in about every 12 years. So, pipes that are 60 years old might not get re-inspected again until they're 72. So we recognize that is problematic, and I will get into that a little bit later on in my presentation. Our sanitary maintenance is also largely reactive. So we don't go out and proactively maintain a lot of our infrastructure. We essentially wait until breaks happen or service calls come in before we really do this. And that's not by choice, that's more by the reality that we live in. And what we're trying to do now is get a little bit more information and data from our system so that we can make more informed decisions around when maintenance actually needs to happen. And again, I will get into that a little bit more as we get into the presentation. And because of, I guess, our current service approach, there's actually several really high-risk elements within our sanitary system. And one of those high-risk elements is our trunk sanitary network, and really the subject of this presentation today. So trunk sanitary sewers, and sometimes they might be called interceptors as well, depending on what municipality you're in. But typically, trunk sanitary sewers are large diameter pipes that receive flows from sanitary mains. They are gravity sewers, so there's no pressurization. And the trunk sanitary sewers are meant to transport sewage to central locations like pumping stations, treatment plants, or even other discharge points. So I often liken our trunk sanitary sewer network to veins in the human body. So if you think of arteries like, the pipes that carry water into the system, and then the arterioles as the distribution mains into the houses, the capillaries are really where the services happen to the houses, where the water is used, then flushed into stormwater mains that then eventually go to these larger stormwater trunk sewers. So when you look at that analogy, on the larger scale of what our our sanitary network looks like, you could see that the city here as a whole has a whole bunch of these lighter green lines, which are our sanitary sewers. And those sewers all at some point will connect via gravity to these larger veins or sanitary trunks throughout our network. And those are depicted by these darker green lines. And what I'm showing here in this figure is only the sanitary trunk network that's larger than 500 millimeters in diameter. We do have other ones that are slightly smaller, but this is the large portion and by far the highest risk portion of trunk sanitary sewers that we have at the city. So today's focus in terms of the case study is really just focusing on one section of the trunk sanitary sewer network, and this is the Ottawa Street Trunk Sanitary Sewer. So that trunk sanitary sewer services a sewer drainage area that's kind of depicted by this red section over here. So there's actually 4 different distinct neighborhoods that kind of drain or get captured by this Ottawa trunk sanitary sewer. That drainage area is about 20 square kilometers, and that represents approximately 20% of the city that's serviced through that one trunk sanitary line. There's approximately 6,500 service connections that go to that trunk sanitary sewer. And, even though that number seems, moderately high, not super high, it's because a lot of this area actually has high rises and multi-residential units. So that multi-residential unit may have, let's say, 200 or 300 people in it, but we only count that as one service connection. So again, there's a lot of connections, a lot of flow that goes through this pipe. Now, the Ottawa Trunk Sanitary Sewer was installed 38 years ago, so in 1986. So it's not that old. It's a reinforced concrete pipe. And to our knowledge, since its installation in 1986, we've had no prior inspection of that infrastructure. So we really didn't have a lot of eyes on this, and we didn't really know the condition or the state that the infrastructure was in. Okay, so now if we just kind of zoom in a little bit to that area, you're going to see a little bit more detail in terms of how that sewage is managed. So in that drainage service area that we have actually 5 pumping stations that operate there. So Otterbein, Springmount, Bancroft, Appletree, and Woolner Trail. So Appletree and Bancroft actually, as pumping stations, pump towards Springmount. So Springmount ultimately receives these 2 pumping stations before it pumps into the sanitary trunk sewer. So again, that just means that, we have 3 major connection points from pumping stations in there, but it's really 5 that contribute to it. On the right of this slide, I've also provided the typical flows that go into the trunk sanitary sewer when these pumps are actually firing. So you can see it kind of ranges between 65 liters per second to 100 liters per second. But combined, you're well over 250 liters per second that are going in at any given point. So here's a kind of a Google image of what the area actually looks like. And what I've done is I've marked the area of the failure in the yellow X. And the direction of the arrow kind of talks about the flow, because I mentioned that the trunk sanitary sewers are all gravity fed. So you could imagine just taking a look at here, how dense and how many houses there are that are all in this area feeding towards this one pipe that runs essentially along the same parallel length of this road. So when you have a break in that one section, you're essentially disrupting the flow for this entire area of the city. So this road itself is Ottawa Street. It's a major street. It's got 4 lanes, 2 lanes in each direction. It's also got bike lanes on it. In and along this area, there's commercial establishments. There's residential, as you could see. And just to complicate matters as well, this break happened to have happened just outside a fire station. So we had to manage emergency response during our time. So this next slide, I kind of zoom in a little bit more on this one area. And here's that fire station I was talking about. And this is the driveway that they kind of go out for emergency response. So you could tell, or you could see, the break happened literally just outside of where that fire station was. So you can see again, this is the 4-lane road. It's a major intersection throughout the city. So a lot of different moving parts in a very inconvenient area for us to actually lose service. So what I'll do now is I'll just kind of go through a timeline of how this failure actually ended up happening. So on February 17th, 2022, we got a few complaints from residents of sewage backups in the area. So we dispatched crews earlier on that morning. Crews spent about 6 hours trying to clear that blockade. So we knew that it was a significant issue. We didn't know exactly where the issue was coming from, but we knew that there was something going on. So that was kind of our first hint. And then so the next day, we got more calls from residents. So the crews returned back to the site again. And again, they did their best to clear the blockage. But they weren't able to clear it enough for us to get a camera down there to examine what was actually going on within the pipe. Now, the reason why I have a calendar here is, we in the service industry often say that, these emergencies only happen on a Friday before long weekend. literally this was a Friday before a long weekend here in Ontario. So, on Friday, we've discovered this. And so instead of trying to address this because we didn't know the full extent because we weren't able to get a camera down, we decided to have crews monitor the flows over the long weekend and respond as needed. So we didn't actually enact any of these larger measures until we did more investigation following the long weekend. So finally, on the Tuesday after the long weekend, we were able to clear the blockage enough to actually send a camera down there. And what we discovered was a massive void in the pipe. So the pipe had fully collapsed. And the reason why the blockages were being created was because all that sand and rock and gravel was getting into the pipe and clogging that pipe. So on this next page, you can kind of see what we had discovered after we had cameraed. And this void is just partially showing just how big that void actually was. So when we finally did excavate, that void was large enough to actually swallow a city bus. So it gives you an indication of just how big the issue was and how big that sinkhole was that was forming. Needless to say, we quickly got our heavy equipment off of that area where it's just kind of floating on top of that void. But as we were kind of excavating and looking at the damage that had been done, we noticed that the concrete pipe that was there typically should have had about 2 inches of thickness on the wall. And that 2 inches of thickness had deteriorated to, less than a centimeter in some sections that were still intact. And then, it had completely broken through on sections that had collapsed. And a large part of the corrosion and the disruption that we saw in those pipes was actually due to hydrogen sulfide gas, so H2S gas. And that's a byproduct of, sewage and stuff that decomposes, especially if it ends up getting stuck inside your pipes or not getting flushed out as quickly, or if you're getting high concentrations of sewage that has H2S gas already in it from upstream. So, we suspected that it was more the latter as opposed to the former. We were likely seeing a lot more of this overstrength sewage getting into this particular section of our pipe. Also, we noticed as well that right on top of the area that had collapsed, there was another 925 millimeter regional storm pipe. There wasn't a lot of separation between the two pipes. So, there's a possibility that pipe being exactly where it was in that location also partially contributed to some of the deterioration and some of the cave-in that we saw on that pipe. Okay, so how did we actually address that repair? After we discovered that there was a massive void, we knew that we needed to get this line back in service. It services 20% of the city. So having 20% of the city, and that would have worked out to, I don't know, I'm trying to do the math really quickly here. Would have worked out to about 60,000 residents. Telling 60,000 residents not to flush their toilets for a few days would have been very, very bad news. So we knew that we had to enact a solution fairly quickly. For us to be able to address that one section of pipe to do a temporary repair required us to stop the flow of sewage that went through that pipe. And as I said, there's about 250 plus liters per second that will flow through that pipe. So we had to bypass all that sewage. So we were able to bypass for about 60 hours from 4 pumping stations. So remember I said, previously that there's 5 pumping stations that service that one pipe or that went into that one pipe. We were able to divert flows and bypass the flows from these 3 pumping stations, Springmount, Bancroft, and Appletree, as well as Woolner Trail. Otterbein, we knew that the flows from Otterbein would have put us over our ability to manage those flows through a temporary bypass. So we actually ended up hauling that sewage for about 60 hours by truck. So we'd get into our pumping stations, pump down those wet wells, and then we'd haul it by truck to the next nearest dump point that we had. So we ended up repairing about a 24-meter section of this sanitary trunk main. And that sanitary trunk main, the limits of that sorry, the reason why we only did 24 meters was that was the limits of our locates. So that was the limits of the information that we had of the other buried infrastructure, which restricted us to doing work only in that area. We actually also, at one point, I think we had every single member of our operations team out there trying to manage this site and manage the work. And we also had to call in for help from our neighboring municipalities who sent equipment and other operators as well. We ultimately had to enact the repair for just approximately 3 days, but the road itself was closed for about a week and a half. And that was due to the fact that we weren't able to restore the road in the middle of winter for a period of time until we could secure some asphalt. So here are some pictures from the actual repair itself. So this is
I'm not seeing your, I don't know if anybody else, but I'm not seeing your presentation for a little while.
On. I'm seeing
It
it.
is on. I'm seeing it, yes.
Oh, you are? Okay.
I'm not
see.
seeing it.
Well, it's not in your, it is in your side. We see the presentation.
Okay, perfect. I'm glad that the presentation's still up. Sorry, Valerie, I don't know what's how to troubleshoot that on your end.
Don't worry, as long as everybody else can see it.
Okay, so I'll continue. So here are some pictures from the actual repair work itself. So the picture on the left here is our bypass. So as I said, we had to bypass the section of pipe that we were repairing. So we were essentially pulling the wastewater out of that section upstream and then running it down a hose that stretched about 200 plus meters to another downstream manhole where we were then discharging. And we were bypassing about 100 liters a second through that bypass. And that bypass was lasting for, like I said earlier, about 60 hours. And that bypass was managed and manned 24 hours a day for those 60 hours. One of the things that I didn't mention previously was that this work was in the middle of winter. So the temperatures on average over that 3-day work was between -5 and -15 degrees Celsius. And that doesn't include the wind chill. So the wind chill factor on top of that, it felt more like -25 to -30. So very difficult conditions to work in, but we were able to get a lot of that work done. And you can see just what type of construction work it was. We had to put some construction shoring in to secure the section and before they were able to drop in a new section of pipe. Okay, so repairs took 3 days. The road finally opened up a week and a half later. Everything went back to normal. Flows were reinstated for the customers. And I would say that this was, more or less a success because during that entire 3-day repair period where we had to bypass, not one customer of that potentially up to 60,000 customers that would have been impacted experienced a disruption in their service. So we've basically, said that was a very successful operation that we were able to do. But after the actual initial emergency response, we really had to kind of pull up our sleeves and do some post-repair investigations to figure out just how much of the rest of the pipe was in bad condition and whether or not we needed to address those other sections. So part of our post-repair investigations was to look at the entire length of this trunk sanitary sewer, which was about 1,700 meters. So 38 sewer sections were investigated. Of that 38, 20 were shown to have severe structural deterioration from H2S corrosion. The remaining sections also were impacted, but those impacts were low to moderate. Now, what we also did was we put in some upstream H2S monitoring equipment just to see what the level of H2S entering that system is, where it inserts through the force main. And what we were seeing were average H2S concentrations were in the 60 ppm range. It spiked to an average range of about 160 ppm, and our peak at any given point was 220 ppm. Now, just to give you an indication, anywhere between 5 and 10 ppm can lead to concrete corrosion. So these are orders of magnitude higher than what we would anticipate having in our system, which would explain a lot of the results that we ended up seeing. And you could see some of these results here in the photos, where, you know, this is kind of moderate corrosion, but you can see some of the severe corrosion of this concrete that was in our system. So these sections were essentially, you know, they were ripe for collapse. You know, they're ripe for failure. And we were just fortunate that that one failure happened that gave us the opportunity here to go in and inspect the rest of this infrastructure. So what does the work actually entail to rehabilitate this? So as a reference point, the emergency works were in this yellow square up here. So that was a 24-meter section. So that work occurred in February 2022, and it cost us about $172,000 for the 3 days worth of work to repair that 24-meter section. What we have now planned to do to address the rest of the corrosion and the rest of the damage to the pipe is to do rehabilitation works this year. So we've already tendered this work. We've been planning it for the last year and a half. It's going to be 1,700 meters of cured in place pipe. And we're also going to address 24 manholes as part of that work because of the deterioration that we've seen there as well. And this project alone is going to cost us about $7 million. So when you start to kind of break down the cost in terms of how much the emergency works cost versus the rehabilitation works, the emergency works just based on a linear pipe segment was $7,200 per meter. And that includes the cost of repair, the temporary bypass, the road restoration works, so on and so forth. Now, for the rehabilitation works, yes, the price tag is $7 million for 1,700 meters. When you break that down in terms of the cost per unit meter, it's going to be about $3,400 per meter. So less than half that amount of work, or sort of less than half the cost. So it gives you an indication that, you know, these emergency works are very costly when we have to do them. And the best course of action really is to try to plan these works out, you know, as best you can. I should also note too, of that $7 million that this rehabilitation works is going to entail, 30% of that cost is actually just in the bypass of the sewage alone. So it's not even laying infrastructure, it's just prepping the infrastructure so that we can actually get the pipes in the ground. So our trunk sanitary network, I often call our ticking time bombs. And the reason why I call this our ticking time bombs is this is just kind of a sampling of some of the major trunk sanitary sewers that we have in the city of Kitchener. It gives you the length and it gives you the material type, which is largely concrete pipe. But this red, sort of this middle column with all the red here, tells you how old this infrastructure is. The really interesting thing is the section that failed, highlighted here in yellow, the Ottawa Street trunk sanitary sewer, it was only 38 years old. So when we were looking at an age and material-based prioritization, it wouldn't even have hit our radar as a major concern. And if you really look at two of the major concerns, we have Montgomery Creek here that's 70 years old about, and the Spring Valley North trunk sanitary that's 77 years old. Like, I mean, this pipe here is 40 years older than the Ottawa Street pipe that we had to do an emergency repair on and now are doing rehabilitation work on. And none of these sections we have any inspection data on. So this is why we call them our ticking time bombs. And again, the trunk sanitary sewers, they're the major pipes that collect all the sewage from certain neighborhoods around the city. So any impact and loss of service on these pipes alone will generate a significant impact back to our customers and our users. So why haven't we done trunk sanitary sewer inspections in the past? And so that's a good question. And we don't have a lot of data because the data has always been very, very hard to gather. And trunk sanitary sewers in particular are difficult because they always have continuous flows, and those flows are always of high velocity. So if you look here at the video that's kind of showing to the right, you can see just how fast that water is flowing, that sewage is flowing. So a lot of the technologies that are out there, where there's camera inspections and things like that, it has a very hard time managing that level of flow to be able to get any detailed information for us to make that assessment. Also, some of these trunk sanitary sewers are also very, very large diameter pipes, so a meter or more in some cases. And because they're so big, some of the technologies that we have, again, are limited in how well they could generate the high resolution images that we need to be able to assess the condition of those pipes. And in our trunks network in particular, some of the access points are very limited. So we could have stretches over 1 kilometer long stretches where the 2 insertion points into that pipe are over a span of more than 1 kilometer. And because of that distance, it's really, really hard to employ certain technologies because certain technologies just don't have the capability to go that distance, that length, especially technologies that are tethered to a system like some sort of drone or a boat. So yes, we've definitely had some challenges in our trunk sewer inspections, but we need to figure out a way to be able to do these inspections because, like I said, these are just ticking time bombs for us. So some of the lessons learned that we have from this failure. So clearly, system monitoring and inspection is a critical aspect and something that we really need to focus on. Corrosion of concrete pipes from H2S gas is a big problem. And we don't know the extent of how much H2S gas is actually in our system. So we need to figure that out to be able to assess just what level of risk most of our concrete pipe is at for collapse and for other failures. And again, I alluded to this earlier, and despite the challenges that we have for trunk sanitary sewer inspections, we have to find a way to inspect this infrastructure because it is one of the highest risk infrastructure that we have in the city. And ultimately, emergency repairs like we had for that 24-meter stretch, they become very costly. So if we really wanted to look at a financially sustainable way of managing our system, we should be looking at proactive repairs and rehabilitations of these sections before they fail. So how do we use this as a catalyst for change? So again, I started off this presentation by, and it's in my presentation title, to say that we never want to let a good crisis go to waste. So this crisis was one that our council knew about. Like they were kind of waiting with bated breath to make sure that no residents were impacted. And because we came through with a good news story, I think everyone was relieved at that. But no one wanted to go through that again. So because of that, we used that as the basis point in developing what we call our water infrastructure program, so our WIP, WIP WIP. So our WIP is really just a large business case that looks at multi-year rate increases or multi-year rate setting for our utilities to ensure that we could develop a plan to have a financially sustainable and robust delivery of our services. So we used this crisis as a case study in this water infrastructure program and highlighting in that program the need for us to prioritize our inspections and our data collection. We prioritize monitoring of our system. And also we wanted to take that information that we're collecting to make better decisions on how to address aging infrastructure or these high-risk sections within our infrastructure. So what we did was we developed that 2024 water infrastructure program through utilizing this case study. And what we were able to do for the first time ever was we were able to get a doubling of our CCTV inspection budget. We were able to introduce a new citywide H2S monitoring program to understand exactly what risks are happening within our system. We implemented a new citywide I&I inspection and reduction program. We implemented a new citywide deployment of weather stations. And we were able to secure 12 new full-time positions, including 5 positions that were to support inspections, monitoring programs, data collection, and analysis. So really focusing our entire approach over the next 4 years largely on how do we collect this data, how do we utilize this data, and how do we make better informed decisions. And we use this, and we were able to get all this based on using the example of this failure or this crisis that we had. So the goals of the WIP ultimately, and I've just kind of mentioned this, is we want to get to data-informed decisions. We want to be able to take that data and help us establish appropriate levels of service. And then ultimately, it's to help us right-size our budgets so that we can deliver these programs in a more sustainable fashion. When we have these emergencies that pop up and when we run infrastructure to failure, we never know what the costs are. So being able to use that data to understand our system a little bit better and appropriately budget for those programs to be sustainable, that's kind of the long-term goal that we need to get to. So key takeaway, never let a good crisis go to waste. So if you have a crisis, yes, you have to manage that crisis as best you can in the moment. But when that crisis is over and you're able to reflect on it, make sure you take that opportunity to take that, use it as a case study, use it as an example, and use that in a way that drives a program improvement later on that either secures you additional budget or secures you a pathway for you to make your system and your utility a little bit more sustainable. So with that, thank you for your attention and happy to take any questions if there are any.
Thank you, Dr. Lam. And I think we have quite a few participants. Please feel free to put your questions. You can
Good afternoon.
Right,
Whole
John.
bunch of planting. Good afternoon. Yes, Mr. Jha, good afternoon. Wonderful presentation, if I might say. One question though. Firstly, it's excellent to know that no customers were affected while you all were doing such a major project. The other thing is, how many trucks, just as an average, on how many trucks in terms of the tankers, sewer tankers, and the vectors, how many trucks did you all actually use to maintain that sort of flow? Because maintaining that flow is definitely a difficult thing to do.
Yeah, for sure. And great question. So what we ended up doing was we had trucks basically leapfrogging each other. So one truck would fill at the pumping station until it was full, and then it would proceed down towards the next depot for it to dump, which was, I'd say, less than 2 kilometers away.
Okay.
And we would then, when that truck departed, another truck would come in and immediately start filling up their tank. And then when the other truck came back, that truck would be full and then it would leave again. So we just had that in a rotation. And I believe that the trucks were large enough for us that we only needed 2 trucks to manage that,
right.
pumping.
Adrian, it's good.
Thank you very much. Excellent.
Yeah, I was really amazed by this presentation. And I always also want to relate it to the relevance to the Caribbean. Although we don't have these large sewer systems, except maybe for Trinidad, English-speaking Caribbean. I still think this was a magnificent experience and solutions. I had a question about the trucks, how you do that, but you answered that already. Now my question is, my first observation was also that it is the newer sewer pipe that corroded, and you don't have this one as the older one. So my first thought was that the newer pipes might be of much less quality. The older pipes might have been better. Maybe some contractor was cutting corners somewhere. But anyway, but that's not. But secondly, before I left to the Caribbean 40 years ago, I worked for a Dutch consultancy, and they had developed a system to repair sewer mains. And it was the mole and sock system. They had a metal, I'm not sure if you know about it, but so especially concrete and deteriorated system, or in the old days, we had also clay pipes, the smaller ones. And a mole would go through it. They could even widen the pipe. And then they would pull a sock of a polyester compound with epoxy. And then they would put it through the pipe, the trunk, and then would blow it up. And then the epoxy would harden. And then you have a very high resistant also to H2S pipe. And then later another machine went in it to drill the holes for the side connects. But you're aware of that system. Or are you using that system to repair your mains?
Yeah, that's the exact system that we're using for the rehabilitation of that 1,700 meter stretch. Yeah, so we call it here cured in place piping, so CIPP.
Cure in place. Okay, yeah.
Yeah.
so you don't have to dig open the road and so.
That's correct.
Yeah.
Yeah. So we don't have to dig up the road, but we still have to manage the flows through that pipe section.
Yeah, yeah, yeah.
That's the challenge.
Very fascinating. So this also gives me an idea for another presentation for a webinar for CAWASA, and that is the case that happened 11 years ago in Barbados of overflowing sewer trunk along the south coast. I would not be capable enough, or I have not enough information or the authority to present that, but I suggest Jean, I'm getting old, Ignatius, to request maybe BWA to do a presentation on that crisis and disaster where wastewater of the whole south coast could not be discharged to outfall, but have to be dumped into the coastal zone, and it's all it was a nightmare for Barbados. But also lessons learned from that disaster might be beneficial for the Caribbean. But anyway, thank you very much for your.
Is that really 11 years ago now, Ignatius?
Yeah, 2014. 2014.
Oh my gosh, it seems like yesterday. But yes, I was thinking of that when Boo was talking, and I know Anderson's with us from BWA. So yeah, it would be a great presentation to have as a follow-up to this. And I think Boo would like to actually attend that one probably.
Yeah,
absolutely.
We were involved in that, in giving some advice. It was a very complex situation because of the pipe on pipe and below water.
Yeah, that was horrible. It was a horrible preventable. But worse is it was all a preventable situation, and it was a design issue, an operational issue, not replacing old pumps. Anyway, except I'm not the right person to talk about it, but I hope that BWA could talk about it in the future, because it's also a lesson for other Caribbean countries that have sewer systems, are planning to install sewer systems, which is a trend. Okay, so it is not a system you can just put in and leave alone. It requires monitoring and repair, maintenance and repair necessary. Okay.
Intervention. I certainly will pursue this with our colleagues at the BWA. And Anderson, take notice that we'll be coming to you.
I'm coming for you, Anderson.
No, but you see, everything is politics in the Caribbean, so who wants to stick out his or her neck, right? Anyway,
we'll see what can happen.
Yes. Any other questions or comments for this on this wonderful presentation?
I want to add. So I want to add that the presentation was so clear. I was able to go on Google Maps and check Kitchener and area, and I even found the place where they did the repair. I took a picture of it, and there is a diamond-shaped space in the road on the right lane. Yeah, and there's a circle in it. That must be the manhole. I see that must be the leftover last part of the repair with a manual to go inside. I found it quite detailed, your description, and I was able to find it on Google Maps.
That's excellent. And there was a manhole, like literally, I don't know, 5 feet away from the section. So you probably found the exact spot.
I found the spot. Yeah, I know this is spot because I could match your video, your map with the Google map. So it is right there. He's not lying. He doesn't make it up. It's really there.
I think someone else was trying to make an intervention.
Hugo from Belize.
Yes, Hugo, please, Hugo.
Really nice to see Belize with us today.
Yeah.
Yeah. I could relive the same situation as the presenter. Now it's a very good presentation. We had similar instances a while back. We have crushed sewer mains, to be exact. What we learned, the same thing, we had to pump from one pumping station to another, ensure that the other pumping station are not overflowing, etc. And it's just a team effort in terms of really addressing that crushed sewer main. Similarly to yours, we had to do excavation and replace the mains. And that is not just one occurrence, but several occurrences throughout the years. And we have practically developed an SOP as to when we have that similar situation arising. Similarly to that, we are looking at CIPP, but because of our lack of knowledge of how that is actually used, etc., we are kind of cognizant to what it entails and how to use it, perhaps assisting us in terms of how that cured in place would work. Because we do have that as a thought, obviously cost is a factor. We do have old sewer mains that we are addressing at the moment, but due to our risk management, which also forms a part of that, is sewer overflow. The overall goal is for us to address it as quickly as it happens. So that's how we deal with it at the moment. But we are looking at CIPP as an alternative to address these crushed sewer mains, especially in older areas which we serve customers as well.
Yeah, so Hugo, I think Operators Without Borders can possibly help you there. So when we're talking in the next couple of weeks, let's add that to the topics.
Right, thank you, Hugo, for that intervention. Any others?
Hi, good day.
All right, Tim. I'm sure you would come on.
Out of Trinidad and Tobago. Just my observation of a photo there of one of the manholes. In terms of the manholes and deterioration by hydrogen sulfide, would you have encountered you know, that type of things to repair and so on? We had some, even the runs in the manhole looked like they would have needed replacements and so on, and probably some sort of a resin on the internal areas there. But do you do that kind of stuff as well?
Yeah, so in this particular case, there's 24 manholes that we noticed were deteriorating. So they'll also be replaced as part of our work. Typically, most manholes that we have are all concrete lined, or not concrete lined, concrete in material. And because H2S gas is starting to present itself as a very significant problem in our system, we're starting to do a lot more inspections on those manholes now across the city, just to see the extent of the repair work that needs to get done. And once we get that information, that'll build out our next water infrastructure program so that we have sufficient budget to be able to address those issues.
Great, thank you. And you guys did some great work in that freezing temperature. I don't think I would have been able to make that.
Yeah, it was a cold one for sure.
Don, is that a latent hand or is that a new hand?
I re-raised my hand because I had another note on exactly on the H2S gases. Is there any way to extract H2S from the sewer system so you don't have all the accumulation and deterioration of the concrete? Is there any project or any possibility to extract with actually venting fresh air and extracting H2S in sewer lines? Has it ever been considered, or is this a new business opportunity?
Yeah, so if we know that it's coming from a point source, like a let's say it's an industrial discharger, there are additives that you could put into the effluent that will it'll react with the H2S gas to reduce it now down to a more inert gas before you then discharge. So for instance, we just ran into an issue where the landfill close to us, they were discharging overstrength leachate directly into the sanitary system.
Yeah.
And it took us a little while to discover that it was them. But when we finally discovered it was them, they had a contractor that they hired that put a additive in to that leachate, and that was able to bring the values of, I think they were somewhere over 100 ppm down to less than 2 ppm.
Because your values are extremely high, so I was wondering. Okay, but you found the source and you dealt with it. Thank you. Wonderful.
Right. Any others? Going once, going twice, going thrice. There have been no others. I'd like to thank you very much, Dr. Boulam, for sharing us your time. Oh, sorry, someone, Hugo has a question in the chat. What's the name of the additive we use to vent
Vent at some location.
at some location?
Yeah, so I will have to get back to you because it's a trademark name and I can't remember right now. I'm gonna have to search through my my emails to figure out what that the name of the additive is. But maybe I'll circle back to Valerie and I'll send you, Valerie, the information. Okay.
Yeah, and get
That's
it to
great.
Hugo.
Well, we'd like to thank you again, Dr. Lam, for sharing your time with us and for this very comprehensive presentation. I think it was very informative and it seems we had some good participation. And I would like to thank Ton and Tim and all the others for their intervention. And also to Valerie, as usual, Operators Without Borders, for finding us some very good guest speakers. And if it's Wednesday, it's CAWASA Wednesday webinar. And today is the 9th of April already, and it is the 9th seminar of the year. And we look forward to you joining us again. Just a little plug for CAWASA. We're just reminding those of you who are yet to register or still collecting the pennies to join us in St. Vincent, June 25th to the 27th for the Caribbean Water Operators Conference. That will be hosted by the TWSA of St. Vincent and the Grenadines. See you then. Have a good evening, everyone, and keep safe. Ignatius Jean, Executive Director at CAWASA, signing off. Bye.
Thanks,
Thank you.
Ignatius.